Hi, all right, welcome to ET370 Lab 2. Here, what we're going to do is learn about serial print or printing things to the serial monitor, and then explore the analog read and analog write side, so the left-hand side of this kind of four-quadrant diagram I have shown. We'll talk about PWM, and then we'll get a potentiometer connected into our Arduino 2 and look at analog read. Okay, so let's begin. So the first thing we want to do is go to Tinkercad here, and we are going to just go and create a new circuit. And let's see here. Yeah, let that go. And we can go in here and go to Arduino and just throw in, let's just throw in the breadboard one again. This was nice, right? So breadboard one has an Arduino, has a breadboard, everything's nicely connected, okay? And what I want you to do is go into code and get rid of blocks, go to text and accept. And we, of course, had the standard blink, program. So now what I want you to do is let's delete out all the stuff in the setup and the loop. So we have just this blank copy of void setup loop, but this blank Arduino sketch. And the first thing we're going to do is type in int x equals 0. And what I've done is now define an integer number of x and with a value of 0. And in the setup, what I'm going to do is type in serial with a capital S, Serial.begin 9600, and open and close parentheses, all with a semicolon. And this will determine the baud rate between, or the bit rate between the Arduino and going back to the computer when this is implemented with your physical Arduino. Right now, this is just the simulation world, but you can change this number to different values. However, the default is this 9600. And then what I want you to do is type in Serial.print ln. So this is ln right here. And we'll print the value x, okay? So serial print out. And what we should see here is notice nothing's connected. We're only looking at the data. This is just doing an internal computation. This is your loop, and it's going to print out this value x to the screen. And it should be very boring. It should be 0. So I'm going to start the simulation, and I'm going to hit serial monitor here, and you can see the number of 0. Right? If I was on the Arduino, like the regular Arduino sketch, I would hit this button here, the serial monitor, and that's what would print to the screen. Okay. Okay, so we got this printing the screen 0, yay. What happens if we choose a different number, like, I don't know, 4, right? So we can try that. And you can see the number 4 print to the screen, right, on the serial monitor. Okay, so this is nice. This tool gives us a way to troubleshoot things, and it's very useful. Okay, so now let's do something a little interesting. Let's go here and into the loop. We're going to type x equals x plus 1, and then give it a delay so that it doesn't just blitz through and flood our information, flood our serial monitor. So I'm going to put delay 1000, okay? And then I'm going to go over here and type in x equals x plus 1, okay? So that way, we can see how x changes. Now, before I even run it, let's give a prediction of what's going to happen. Well, we know what this delay does first. That's easy. We've seen that before in Blink. It's just going to make this program wait here 1,000 seconds before, or 1,000 milliseconds before it continues. So it'll slow down the rate. Now, what is this? Now, you might think of this as an equation, right? And you're like, x equals x plus 1. That equation that doesn't work. Well, don't think of it as equation. Think of it as an assignment. I am seeing the right side, and I'm assigning whatever value the right side is to the left side. So here, the order of operations is actually right, then left, not left then right. Okay, so the very first time x will, let's go back to 0 here, is 0. When it gets to this line 11, the new value of the right side is 0 plus 1, which is 1. So the new value of x becomes now 1. X gets overwritten, so it's no longer 0 anymore. It's 1, and then what will print to the screen is the number 1. Okay, you wait, you go back to 16, it's the loop, you go back to line 10, then 11. Now this is a 1, so the new value of x becomes 1 plus 1, which is 2. And so 1, 2, 3, 4, so on and so forth. This is what we call an incrementer here, and what I'm going to do is run this, and you should see 1, 2, 3, 4, so on and so forth get sent up to the serial monitor. Okay, so I hope this is pretty intuitive. Okay, what happens if we change this value here? What if we make this a 2? Let's see what happens. So I hit start and we go 2, 4, 6, 8, counts by 2, right? The incrementer is 2 now. I could do something like 5, right? Okay, so 5, 10, 15, so on and so forth. Okay, and of course you could also play with the initial conditions. I could start this off at the number 10, right? So it starts off at 10, 15, or I could even start at some weird number like 23. And so I get 23, 28, 33, right? So you can play with all these different things and just see, predict what'll happen and then test it. Okay. What happens if I go here, type in 0, and I put in -1? So -1, let's see what happens. Okay, so when I put that in, start here, I go 0, -1, -2. So it'll not only increment, but it'll also decrement. And so the sign here tells us which way it'll go. Okay, not too bad. All right, so I now have a way of doing addition and subtraction, but what if I do multiplication? So let's change this to 1, and let's do x equals x times using the asterisk 2, right? So the first value be 1, then it's 2, then it's 4 and 8. Let's try it, make sure that that is gonna work out. 2, 4, 8, yep, good, 16. Let's keep going, let's just see what happens. Okay, 256 is growing quite rapidly. It's doubling every time, right? And what I hope you see is bang, after this number, it starts failing. It's like, what's going on here? 16,000 minus 32,000. This is garbage, right? Well, what's happening is that this variable is defined as an int, and this integer, so if we go to int Arduino here, we can see that int Arduino shows that the maximum number is only 16 bits, where 2 to the 16 is only 64,000 values. And because they cut it in half, you get only 32,000. Okay, so you get a maximum of 32,000. So once the number that you're trying to represent passes that 32,000, it can't handle it anymore, right? And so you get this overflow issue. Okay, what you could do is try going to a long. So a long is a different data type. So instead of 32,000, we can say, let's say we go long Arduino. And let's see what we got going on here. Long Arduino, it allows to 4 bytes or 32 bits of information. So you can go up to 2 billion, right? And we can try it. So let's go here and make this a long, and then see when it fails. But it should fail after 2 billion. And yeah, you might think, oh, this is a little slow. It'll get there very, very quickly, because when you double, that's huge in terms of the growth rate. Okay. So 4,000, 8,000, 16, 32, good. 32,000 didn't fail, 65,000, 131,000, right? Okay, well, it's going there pretty quick. And any minute now, any second. There we go, it fails, boom, okay? So I hope you get a sense of what's going on here with this serial print. You can see this loop going over. You have an understanding of incrementers, both addition, subtraction, multiplication. Okay, and what I want to also point out is that what if you want to represent non-integer types? Well, if you want to represent non-integer types, you can use this thing called a float. Okay, so if I would put a float and I put in 1.2 here, it'll be able to handle that, right? So 2.4, 4.8. Okay, so these are important little concepts where you might have to change the data type to make sure everything matches. Okay. Okay, what if I want to print more than one variable, right? And what if I want to print in a nicely formatted way? So let's try something like this. Let's go here and define something like int y equals 3. Okay. And what I can do is this, Serial.print. Now notice print without an ln. I'm going to say y equals, and notice the parentheses, right? I have the, the quotation marks, okay? And this is just the text y equals. Now I'm going to do serial print y, the variable. So that'll show me the number. And then I'll do the same thing for x, right? X equals, all right? And here's what's nice. Notice the pattern, no ln, no ln, no ln, but the last line has an ln. And when I print this out, I have this nice formatted line, y equals 3, x equals, you know, the variable x, okay? You could even play with things like y equals y plus 1, right? So do this, okay? But this, I hope, is a nice way, a little tool that I want to show you. Well, how would I print out data, troubleshoot stuff, and still know what I'm talking about? Is it a requirement to have x equals and this y equals? No, but it just makes everything formatted nicely. Okay. All right, great. So that was the first part of this lab. Now let's go into the second program here. So here we are going to look at the left side of this quadrant. Before last week when we dealt with button and blink, we dealt with the right side, digital read, digital write. Now we're going to deal with analog read and analog write. Okay, so the first thing is analog write. Analog write. Well, what does write mean? From the perspective of the Arduino, write means out of the Arduino. So I'm going to turn on and off an LED. Well, not just turn on and off an LED, I'm going to turn it on smoothly, right? So before with digital write, we had either high or low, but with analog write, we're going to go some value between 0 and 255, where 255 corresponds to 100% brightness of the LED. Okay, now we are going to use this concept called PWM, pulse width modulation. We mentioned that in the lecture, okay, but just to remind you, let's say the Arduino, one of these pins can only output 5 volts, right? It can't do like 3.3 volts, but we can cycle the on time. And notice these pins here, curly bracket or curly tilde, tilde, tilde. We can only use these pins with the tilde to enable this PWM feature. So we're going to use pin 9 here, okay? And notice as the duty cycle, which is the ratio of the on time to the PWM period, as the duty cycle changes, I will have a synthetically larger voltage that my LED will see. And you can see here's an example of 100% duty cycle, 75% duty cycle, 50, 25%, 0%. And notice the numbers in here, 0, 64, 127, 199, 255. When I have 127 as my number for this argument, or this argument, I'm going to get a 50% duty cycle because that's half of 255. Okay, so let's install an LED with a 220 ohm resistor. And what we're going to do is grab the fade program and also put an oscilloscope. So I'm going to walk you through how to do that. Okay, so let's go here. You can either start a new one or you can just delete this. But let's not worry about the code for right now. We're going to go here and again put in an LED. So we're going to go to components here. Let's put in a resistor. And let's make that resistance 220. And make sure that's ohms. And what we can do is rotate it, rotate, 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 good. And I'll put this guy here. And let's get an LED. Is there an LED available? Nope, I'll just search it, LED. Okay, perfect. Okay, LED, let's put the LED in here, easy. And remember, this is the anode side, and I'm gonna run pin 9. So let's see, pin 9, boop, boop, here to here. Okay, good. So I have my nice LED, and then I got to go from here to ground. Okay, so this should go 9 through the resistor, LED back to ground. The other thing that's really cool about this Tinkercad is it has an oscilloscope. And so here's the oscilloscope here. You can just start searching, it auto-completes, finds your oscilloscope. And what we're going to do is we're going to put this oscilloscope here, and I'm going to monitor the voltage between pin 9 and the ground. So I'm going to take this negative terminal and then go here, here, here to ground, and I'm going to take this positive terminal and go all the way to pin 9 over here. Okay, nice. All right. The last thing I'm going to do is I'm going to go to my regular Arduino and I'm going to grab the fade sketch. So file, examples, basics, fade. Okay, file, examples, basics, fade. And I'm just going to literally Control A, Control C, copy this fade program and dump it, overwrite this code. So delete everything and just dump it here. Okay, when I run this, okay, what's going to happen is you're going to see the nice PWM signal here on the oscilloscope, and you're going to see the LED fade in and out. Okay, now one thing, this is kind of passing by a little too quickly, so I can go in here stop the simulation and set this down to, let's just try 1 millisecond. Okay, as the time per division. So each one of these blocks counts for 1 millisecond and rerun it. Perfect. Can you see how the LED is fading in and out? And when it's the brightest, the duty cycle is the highest, right? And that's pretty cool. That's pretty cool. So hopefully this is definitely a visual of PWM in action. Okay, and so we've just done program 2 here, right? We have our current limiting resistor pin 9, right? Okay, so now let's just look at this code. Let's look at this code. So we're going to go back to the code, stop the simulation, and let's just figure out what's going on. Okay, we got our comment sandwich here. Good. Int LED is 9. Okay, so that is the LED pin. We've seen this before in Blink. Perfect. We have brightness. So this is going to be the duty cycle, and this is going to be how bright the LED is. And this is going to cycle between 0 and 255. And then we have the fade amount. This is going to be like that incrementer, the x equals x plus 1. This is like the 1, right? That fades up and down. Okay. Now in the loop, let's see what's going on. We have analogWrite. Good. We are telling the LED pin, which is pin 9 in this case, to go be at a certain duty cycle. In the first instance of this loop, it'll be 0. So it's actually turning the LED on with 0 duty cycle. So it's just essentially off. The next thing it's going to do is it's going to increment. We saw this, x equals x plus 1. Well, this is brightness equals brightness plus fade amount. So this is equivalent to x equals x plus 5, right? Because fade amount is 5. Okay, so if you just have these lines of codes, every time this operates, this executes the loop, what's going to happen? Brightness is going to be 0, then 5, then 10, and it's going to keep going until it surpasses 255. Right now, if the maximum value of this analogRrite is 255, we would have overflow issues, right? So we need some way of detecting when brightness is too much and switching the direction. Well, that's what this guy is for. Now let's look at this very carefully. We have an if statement, so we have parenthesis, parenthesis, curly bracket, curly bracket. If brightness is less than or equal to 0, and look at this double vertical bar. So this is right above your enter key. It's the shift slash, the double vertical bar here, or brightness is greater than or equal to 255. If either one of these are true, what it's going to say is make your fade amount equal to negative fade amount. So let's run through an example. Let's say fade amount was 5, positive, and your brightness was 250. Okay, so we got 250, turns on the LED near 100%. So then it runs this line, 250 plus fade amount, which is 5, becomes 255. Then it goes in here and it goes, wait, is this true? No, but is this true? Yes, this is, right? Because bright 255 is equal to 255. Yes, so it goes in here and it says fade amount equals negative fade amount. So now fade amount is negative 5. It cycles through the loop, and then it still gives 255 here, but the new value of brightness is now 250 again. So it went from 255 down to 250. And now it goes into here. It goes, well, if I'm at 250, are either of these met? No, none of these are met. So it doesn't do this. It skips over these curly brackets and then keeps decrementing. So 250, 245, 230, or 240 and keeps going down. And what happens is this brightness is going to go up and down and up and down. Can we use our Serial.print stuff to actually see this? Well, sure. What do we got to do? Go back to our setup and type in Serial.begin 9600. Okay, and watch this. We can come in here and we can type in Serial.print, and I'm going to say brightness equals, just so that we have our nice formatting, and Serial.println and brightness. Okay, and so what I'm hoping to see is that this brightness actually goes up and down. So let's run this, and we're going to see this in the serial monitor. Check it out. Look at brightness going up by 5s up to 255, and then look, it starts decrementing after it hits 255 as predicted by lines 39 through 41. And when it gets to the bottom, notice it once it hits 0, it comes back up again. Okay, and so all these numbers are corresponding to each other. So this is very nice. Okay. Okay, good. So I'm going to stop that simulation and let's look at what we got next. Okay, so we completed this, the second program. We're now here on the third program, right? We're looking at brightness. And what we also want to do in this third program is go, well, what happens if we change the rate of fade amount? Can we change fade amount? Okay, so what if we make fade amount equal to, let's say, 11, right? So what's going to happen to brightness? Right? So you can see it's counting up by 11, right? But it still works. This is nice, right? And it still works because you have this greater than or equal to 255. And so let's see if I can pause it just at the right time here. Notice we get to 255, 264, but then it detects that 264 is greater than 255 and makes fade amount go backwards, right? That's good. Now, what if we had put something kind of unintelligently? We put equals equals here, equals equals. So this is asking the question, is brightness equal to 255? What would be the problem? Well, the problem is if you haven't chosen fade amount to be a multiple integer, a multiple of 255, it would just pass this and never flip around. Let's try it. So we tried 11, okay? Look at this. Watch what's going to happen. It just keeps growing. This end condition never got met. And what happened? It just keeps blowing past. Okay, so this is a problem here for, what do you call it? For fade amounts, not a multiple of 255. So the original way was a much better practice because what it's detecting is if there's ever a case where this value was greater than 255, it would also catch that. So this is a much more robust way of coding this in. So let's put it back, greater than equal to, less than equal to. We are good to go. And let's double check. We're going to run that again. Okay, counting by 11. Yep, it goes up, it goes down. Perfect. We are set. Okay, so let's set this back to 5 just so that we're still at the original state. Okay, so everything is good and we're racing through this. We finished the first, the second, and third part. Now let's go to the fourth program here. And in the fourth program, we're going to take in this analog data using a potentiometer. So you should have this, but let's add a potentiometer. Okay. And this is going to take advantage of our analog read. So if we go back up here, we're now going to be in the top left quadrant here, analog read. Okay, so the potentiometer, we're going to go over here, move this code box out of the way, and I'm going to type in potentiometer here. Okay, let's see, potentiometer. Oh, perfect. And I'm just going to put that right here. Okay. Now, typically a potentiometer is one big resistor where you can move this dial in between here. So we're going to take one end and just tie it to ground, and the other end, we're going to tie it to 5 volts. Now, the middle end, we're going to have it run all the way to not digital pin 2, but analog in 2. Okay, do you see me running it all the way over here? Okay. I could have chosen any of these analog ins, but I just happen to choose 2. Okay, so what we can do in here is actually take in this data and we can follow our sheet here, right? So yep, A2, very good. And what we're going to do is we want to record this potentiometer setting. And don't forget, we're using a voltage divider like principle, right? The voltage that goes to pin 2 is now going to be somewhere in between 0 and 5 volts, depending on the dial here. And we're using our ET250 analysis. So go back to the voltage divider lecture, watch that again, but it should be a pretty straightforward voltage divider relationship. Okay, so let's take this in. What I want to do is I want to define, and let me just make sure I'm following the instructions you have. I want to declare using a float pot data equals 0. Okay, so let's put that here. Float potentiometer or pot data is equal to 0. Okay, and then I'm also going to define a int pot pin is equal to 2. Okay. Now, what's nice about the analog ins, it knows 2 is going to be A2, and it doesn't require a pin mode input for for the analog in. It already knows it has to be an input if you're using this side. So over here, I can say this. I could say pot data is equal to analog read this time of pot pin. And this should look very similar to button. Remember, button state equals to digital read of button pin. This is the same thing. Pot data equals analog read of pot pin. What's pot pin? Pot pin is 2. Okay, and it knows, the Arduino knows that 2 is not the digital I/O 2, it knows it's the analog in 2, okay? Because if you're using an analog read and you see 2, it goes, well, obviously you're not meaning this, right? Okay, the other thing we want to do is actually serial print this data, okay? So we are going to put these 2 serial print lines above the brightness one. So let's just do this. So we have Serial.print, and we're going to say, what is this? This is going to be pot data. So I'm going to use that nice formatting trick. And Serial.print and pot data. Okay, and we saw this before in the first part. So notice pot data is just running. It's not changing LED delay or do anything, but let's just see it print to the screen. Okay, so we got our brightness cycling up and down, but look at pot data, 0, but watch this. Notice the number increases as I move the dial all the way up to 1023. So when the dial's up here, this is reading 5 volts, but 5 volts corresponds to 1023. And if I move it to 2.5 volts, it's going to be 512-ish. And then when I go all the way down to 0, 0 volts is 0. So we have a nice way of actually measuring in an analog signal. This is cool. Okay. All right. Now what's next? Let's see if we can change the rate at which this program goes. And yes, we have 2 ways. One is we can change fade amount, or we can change this delay. And right now this delay is set to 30 milliseconds, but let's change it. Let's do this. Let's say delay, LED delay. And what we can do is define it up here. So float LED delay, okay, equals 30. So now we've just made this a variable. LED delay 30. Nothing should change. It should just still increment. Yep, everything behaves the same. Okay, no problem there, right? But if I go in here and look at I want to change, let's say I want to change LED delay such that as my pot data moves, the LED delay moves. So in the loop, I just want you to literally type in this line, LED delay equals pot data, right? So I'm going to stop the code. LED delay equals pot data. So I can go over here and I can say LED delay equals pot data, and let's print it. Serial.print LED delay equals and serial.print LED delay. Okay, so what have I done? I've said LED delay, very simple, is the same as pot data. And I'm printing it out, right? Okay, and what we should see is just a 1-for-1, but we should also now see the whole program slow down and speed up. So if the potentiometer, look at the potentiometer, it's at 20, right? It's moving, but very slowly. But as I go down here, it should move faster, right? It's trying to move as fast as it can, right? Okay, let's double check. Is this moving fast? Yep. But when I go over here, if I go way over here to pot data of 1023, this is moving super slowly because it's waiting nearly a second, right? It has to wait a whole second for it to increment fade amount. Okay, super slow. Look at this, updates every second, slow, slow. Okay, and if I go over here, let's go to 512, it increments faster every half a second now. Okay, but then if I go all the way over here, it's trying to go as fast as it can. Now, it does still seem slow, admittedly, and that's because we have these serial prints in here. These serial prints actually cause things to slow down. I'm actually curious, I haven't tried this, but I'm curious if in the simulation it actually has, let's see, if I don't print any of this, I'm just curious if I add comments, does it actually run faster? Because in your real code, it will. So let's try this. Yep, it runs, it seems to run faster, right? See, it goes up and down a little bit faster. Okay, it's still constrained by fade amount, how fast fade amount goes, but it's going to cycle through this as fast as it can. Okay, all right, so let me put these back in here. So no longer is the delay slowing it down. Okay, good. So what do we want you to do? So that was program 5, pretty straightforward. And I just want you to note that LED, of course, is very slow for large values of pod data. What we want you to do in your homework is very simple. It's very, you just need to modify this equation here, right? Or this assignment, I should say. We want to modify this assignment such that LED delay is 55 when pod data is 1023, and LED delay is 5 when pod data is 0. Very simple. Make sure that you have any numbers that you are computing have a decimal point and a 0 in here. Otherwise, it'll get confused because it'll think you're operating with integers instead of floats. And right now, LED and pod data should be floats. Let's double check. Yep, pod data and LED delay are floating point numbers, which means you're happy. So in your homework, go and modify this equation, implement on Tinkercad and your physical Arduino, and submit this. All right, I hope this little video helped and that you learned something. Okay, see you at the next one.